So it is recorded and it will be available on Learn Upon soon. During the webinar, you can also type your questions in the Q&A chat box, and Monica will answer them in writing. So today I'm going to hopefully have the time to answer 26 questions that you have on the MonolixSuite that cover all these topics. So some questions are just on the available documentation, and we have many questions on population modeling in Monolix, focusing either on the structural model, the statistical model, algorithms and tasks, results and plots, and also some questions on advanced models, so how to model some situations. And then we have a few questions on simulations in Simulix, how to script the MonolixSuite in R with the lixoftConnectors, and finally we have a question in PKanalix. So let's start right away with the questions on documentation. So the first question someone among you asked is whether we have online demos detailing the MonolixSuite software. And the answer is yes, we have more than 200 videos that show how to use the MonolixSuite in many different situations. Some of these videos are full case studies, and some are short tutorials from our Feature of the Week series of videos that explain specific features. And you can find the full list of these videos on our webpage, Lixoft University. That looks like this, where they are sorted by topics. And you can also find them all on our YouTube channel. On the same topic, someone was wondering where to find some examples of PKPD workflows or tumor growth inhibition modeling workflows. So in the case studies section of the Lixoft University page, you can find a full PKPD workflow, so a full case study showing a typical PKPD workflow here in this section. And we also have 3 webinars on tumor growth inhibition modeling that include some examples shown as demos. Another similar question is for a lifespan model. So I admit that this one is a bit more difficult to find as it is a more advanced and less common type of models. But we do have a documentation page whose link you can find here that gives an introduction on the lifespan-based indirect response models that are models that look like this, where the inhibition rate of a cell population corresponds to is equal to the production rate, but with a delay. And we also provide on this page some examples of MLX1 codes and simulations for different types of lifespan models. So we have models for when drugs affect the production rate of the response, or for drugs that affect the cell lifespan distribution, and also an example of a model with a precursor pool. And in addition, we showcase the use of lifespan models in 2 Feature of the Week videos. So number 26 that focuses on using delays in the MonolixSuite, and the video number 81 that shows an alternative implementation. Someone else is wondering if there is any virtual basic learning, and I am glad to take the opportunity to mention our free courses that take place every year to train people on the MonolixSuite. So first we have our Spring School, which was 2 months ago this year and has now ended. It focuses on basic modeling and simulation with the MonolixSuite. And then we have our Summer School, dedicated to NCA, bioequivalence, and more in PKanalix, and our Autumn School, which is for advanced pharmacometrics, so advanced population modeling in Monolix. And for these 2 schools, the dates for this year, 2024, have not been announced yet, but stay tuned if you are interested in registering to these schools. And now I will answer more technical questions, starting with some questions on writing structural models. The first question is how to introduce a lag time in response in the turnover PD model. And the person who asked that question tried this equation with that uses a delay function and said that it didn't work. So here I show you an example of a simple PKPD model that uses this delay function. So for this structural model, I have written first the input list of parameters, the PK part of the model as ODEs, so with the depot macro that links the doses from the data set to the target variable CC, which is the drug concentration. Then the ODE for CC, and then the PD part of the model uses the same equation that was given in the question with the delay function. And this actually works because the CC variable is defined via an ODE. So this is a constraint of the delay function, which is a macro provided in amniotic that defines the variable that is given as argument with a delay. And here the delay is TR, it is estimated as a parameter. But the variable given as first argument has to be defined with an ODE. It cannot be defined with a macro or with a direct equation. And this constraint is specified in the documentation page for the delay function. That was the trick. Another question on this topic. If you have two types of PK data, for example, plasma and amniotic fluid or plasma and CSF, how should the model text be modified so that both types of observations can be analyzed by the same PK model? So again, here is a simple example of a PK model that corresponds to the question with two outputs, C plasma and C CSF. And this PK model has been defined with PK macros. So we use compartment macros to define compartment 1 and compartment 3 that are associated with C plasma and C CSF. Then we use the peripheral macro to implicitly define compartment 2 that corresponds to the peripheral compartment. Then absorption and IV macros to define two routes of administration on compartment 1. This is just an example that corresponds to this scheme here. And elimination macros to define eliminations from compartment 1 and compartment 3. And finally, we use a transfer macro here to define the transfer rates between the plasma and CSF compartments. And then as output, you can choose any variable from the model. So here we choose C plasma and C CSF as output to be mapped to the observation types in the dataset. Now, a last question on writing structural models is how to define a two-compartment PK model plus an effective compartment connected to the central compartment using ODEs in American language. And the person asking the question said it can be done easily using macros, but if I want to introduce a threshold concentration above which the drug can enter the effective compartment, something that looks like this, it is difficult to use macros. So actually, it is possible to include this type of threshold in the model written with PK macros, and it looks like this. So again, you would have the usual PK macros to define the central compartment, to compartment 1, the administration and elimination, and the peripheral compartment. And then you can use the effect macro to define the concentration in the effect compartment, CE, with the transfer rate KT. And this effect macro is documented on this page here. And then the transfer rate can be applied conditionally to the threshold on CC with an if-else statement that you can see here. And this would work. But if you prefer to use ODEs, here is the equivalent model with 3 different ODEs for CC, so the concentration in the central compartment, CP, the concentration in the peripheral compartment, and CE, the concentration in the effect compartment. And here, I can use the same if-else statement to define the transfer rate conditionally on the threshold. And here I have used the parameter for the concentration threshold that is in the input list, but actually you can also write directly a number if you prefer. All right, so that was it for the structural model. Then we have a few questions on the statistical model. So the first is, why do we log covariates and how does it differ than without logging them? So indeed, when we show demos of PK or PK-PD models, we usually log transform the continuous covariates before using them to add covariates effect in the statistical model. And the reason for that is that if we do not log the covariates, then the covariate effect is a linear relationship between the parameters, so for example here V, and the covariate, for example, here weight, in the Gaussian space. So it would be a linear relationship for a normally distributed parameter. But if we have a log normally distributed parameter, such as V here, then it corresponds to an exponential relationship. But the usual relationship for continuous covariates, so for continuous covariates effects, the power law relationship that looks like this. And in order to define this instead of the exponential relationship here, it is necessary to log transform the covariates. So here to define the log of weight divided by a typical value instead of weight. And this can be done in the interface directly. And it looks like this by giving a formula. On the same topic, there was another question. Why does adding a log transformed covariate, for example, the log of creatinine clearance on the clearance, improve the model while the correlation between both is linear? So actually, well, the correlation between the parameters and the covariate really depends on the cases. Sometimes we can see the correlations between the logs, and sometimes we can see correlations that look more linear, but it really depends on the data. So what we can say is that power law relationships for continuous covariate effects are more commonly used. But you can also have a look at the shape of the relationship between the parameter and the covariate on the plot of parameters versus covariates in Monolix. You just have to be careful that usually the parameter is transformed if it is a log normally distributed or logit normally distributed. And you can see the shape of this relationship. But it is really possible to also use a linear relationship if the correlation seems more linear. Then the question we often have on the statistical model in Monolix is it possible to use a customized error model in MLXtran? This is indeed the limitation of the statistical model in Monolix that you have to be aware of. It is only possible to define the error model among a finite set of options that are shown here. The advantage is that it is very easy to define it because you just have to specify the distribution that you want for the observation model, so either normal or logit normal or log normal, and the error model. With just two drop-down lists, you can define all these options. When you keep the distribution as normal, you can choose among all these four choices. So for a combined two error model, the corresponding formula looks like this, where dv corresponds to the name of the observations, so with the residual error, and CC would correspond to the model output. So here the drug concentration without the residual error. And we add on top of it a residual error that looks like this with two parameters, A and B. And E corresponds to the normal random variable that is the residual error. Then if you choose the proportional error model, the formula looks like this, with just the parameter B. The constant error model uses only the parameter A. And the combined one error model has a slightly different formula like this, combining A and B. And then if you choose a log normal distribution for the observation model, you can also use the constant error model, and you get this formula that actually corresponds to an exponential error model. These are the different options in Monolix. Now let's look at your questions on algorithms and tasks in Monolix. The first one is, if while running the model, the error message Fisher matrix is not correctly estimated occurs, so that corresponds to a warning that you can get that looks like this, what could be the reason and how to deal with that? So this message means that the inversion of the Fisher information matrix that we use to calculate the standard errors has failed, and it has resulted in nans in the standard errors. And so you get nans, you can see this nan, for example, in the table of population parameters. For instance, here we see nans for two parameters, V2 and omega Q. And you can also note that you have some very high standard errors, for instance, for QPOP, that has a standard error that has been estimated very high and that is shown as infinity. So nans as standard errors often appear when the model is too complex and some parameters are unidentifiable. So first, it's a hint that you should check that the parameters are identifiable, or you should try to improve your model to make them more identifiable, or maybe remove some parameters. But if you really want to try to circumvent this issue, You can try to increase the number of iterations in the settings of the standard errors task. So the settings can be found next to the standard errors task button here. It opens this pop-up, and you see the default minimum and maximum number of iterations that are 50 and 200. This means that the Fisher information matrix is estimated using 50 individual parameters sampled from the individual conditional distributions. And if the matrix inversion fails, then more parameters are sampled to try to improve the calculation and get a matrix at the end that has no nans. So we add more samples until 200 samples are reached, and then the sampling is stopped. You can increase the maximum number of samples there, but you have to keep in mind that if the Fisher information matrix is really poorly conditioned, it might not solve the issue. Or another method is to use the bootstrap as an alternative method to estimate standard errors on all the bootstrap estimates. And this method is now included in the interface of Monolix in the version 2024, but you have to be aware that it takes a lot of time because it requires to iterate over many replicates of the estimation. Next question, what is the difference between the BIC, so the Bayesian information criterion, and the corrected BIC, and which is worth looking at when comparing models? So I have shown here the formulas for the BIC and the corrected BIC that are also explained on our documentation here. So the formula for the BIC corresponds to the log likelihood, -2 times the log likelihood, penalized by a penalty that depends on the number of parameters in the model n, and the number of subjects n in the dataset and the number of parameters p. The BIC has been derived initially in the framework of fixed effects models, so without taking into account random effects. But it is commonly used also for mixed effects models, where for P, we take the total number of parameters, including the random effects. In contrast, the corrected BIC uses a penalty that is based on not only the number of subjects, n, but also the total number of observations in the dataset, n tot. And we apply this penalty. These two penalties are applied depending on the number of fixed effects parameters or random effects parameters, the parameters that consider some variability. And the corrected BIC has been derived into the framework of mixed effects model. So it is more precise, and especially when comparing covariate models. And that is why we recommend to look rather at the corrected BIC. And this is a value that we report, for example, in Psychomo to compare different models. Next question, what is the relative, that is a bit related to this, what is the relative influence of model fitting on the corrected BIC computation? And the person asking this question says, despite superior fitting in certain cases with the constant error model, the corrected BIC remains substantially lower for the proportional error model, which prompts Monolix to recommend switching to proportional or combined error models. So why does this occur? So this situation can happen that it looks like the constant error model gives a better fit, but Monolix still recommends or gives a better BIC for the proportional error model. It's not always the case, but this is a situation that can happen. And it can be explained by looking at the formula for the log likelihood that we need to calculate in order to calculate the BIC. So here you see the formula of the log likelihood in the example case where the observation model looks like this. So it is composed of a normal distribution and a constant error model. And here F corresponds to the predictions from the structural model. And we have a constant error model here. So in that case, the formula for the BIC for the likelihood looks like this. So you see that it is based on the differences between the predictions from the model, so that is the function f here, that depends on the individual parameters psi I, and the observations y. And these differences are divided by the residual error a. So this means that the constant error will try to have the smallest deviation between the observations and the predictions, While if you replace A here by the proportional error, it will actually add some weights to allow more deviations for large concentrations than for smaller ones. And you could say that it is similar to finding the smallest deviation looking at the data on log scale, so putting more weight on the lowest observations. And that's why you can have a difference between what you expect and the result that you actually get. You have to note that human visual appreciation of a good fit will often focus on only part of the data that the users consider more important. But the likelihood considers all points equally. So that's why we can sometimes have a false impression. All right, next question, still on the log likelihood. What is the difference between importance sampling and linearization? So these two methods, importance sampling and linearization, are the two methods that are available in Monolix to calculate the log likelihood and the information criterion, such as the AIC and the BIC and the corrected BIC. And the difference between these two methods is a matter of precision and computational efficiency. So indeed, the log likelihood is the probability of predicting the observed data Y given the population estimate theta. However, to predict the observed individual data given the population estimates, we need to solve this equation in order to get Y1, and this equation corresponds to the structural model F that depends on the true individual parameters psi I. And these true individual parameters are unknown. So the linearization method uses the EBEs instead of these true individual parameters that are estimated in Monolix. And so we say that it linearizes the model around the current estimates of the parameters. And this is a faster method that approximates the log likelihood, but it can be useful for quick evaluations or when the model is relatively simple. Then importance sampling is a more precise method because it uses instead a Monte Carlo procedure to integrate over all possible values for the individual parameters psi I. And it takes much longer because of these iterations to integrate over the values, but it is more reliable, especially for complex models, and it's important to use this when you need a high degree of accuracy for the likelihood. And you can note that these two methods are described in details in these two feature of the week videos, number 147 and 150. So I hope that this was clear, but if you want more details, you can. I encourage you to really watch these videos where it's all explained in details. Now we have some questions about results and plots in Monolix and how to interpret them. So the first one is, which time grid is used in individual model fit predictions? So this question is about the individual fit plots in Monolix that looks like this. And indeed, you may notice that when you export the chart data from this plot, and you go so to the output files in the results folder that you get corresponding to these plots, you may see a time grid in this file that corresponds to the time grid used for the prediction, so the purple curve here, that counts many time points that are very close together at the beginning of the grid, so close to zero if your grid starts at 0. You can see here this many times here. And this is done so that you can still get a nice looking curve if you choose a log scale on the x-axis, like here. So that's why you have these points that are so close together. And the size of the grid depends on the value defined in the settings of the plot task that you can access here. This opens this window here where you have the size of the grid here. So this means that the grid will contain not only these points, but also all the observations and the dose times for this individual. And it will contain n-2 points, with n being this value, in between the first and last points in the grid, with half of the time points that are taken with the same distance between each other with the x-axis on linear scale, and half of them are taken with the same method but on log scale, which ensures that we still get a nice looking curve when we take the log scale on the x-axis. That explains why we have this strange time grid. Next, so in your Monolix videos, you usually log the X and the Y axis of the observation versus predictions plot before interpreting it. Why is that? So indeed, when we show demos, usually of the PD data or PK data, we would very commonly take the log scale of this plot. And this is because with PK data, we often have many low observations. So if we keep the linear scale like here on both axes, and all the low observations that would correspond to the start of the absorption or to the elimination phase are packed all together, and it's a bit difficult to see if there is any misspecification there, so if they are close to the diagonal or not. And so that's why using the log scale like here helps to distinguish them better and to see the misspecifications. For example, here, it allows to see that there is a misspecification caused by a missing nonlinear elimination that we cannot see in linear scale. Another question on the plot: how can I interpret the scatter plot of the residuals and how to compare it between models? So you can see here an example of the scatter plots of the residuals. We show in Monolix several plots where the x-axis corresponds either to time or to the model output, the variable from the model, and different types of residuals on the y-axis. And basically, you have to keep in mind that these residuals should be scattered evenly around the horizontal zero line. And to see this better, we provide the VPC presets that will show each of these plots. For example, here the NPDE versus time that corresponds to this plot here. It shows this plot as a VPC, so with where we can better see the discrepancies between the observed percentiles, that are the blue curves, and the prediction intervals for these percentiles, that are the blue and pink areas. And the discrepancies are shown in red, just like in the VPC, so it corresponds to misspecifications in the structural model, or the error model, or the correlate model. Another question on the result: when building a model to reach the final model, what do we need to compare between models to make sure that this is a better model, that the final model is really better? There are lots of diagnostics. Do all of them need to improve? And we cite in particular the RSCs, relative standard errors, the VPC, likelihood, scatter plot of residuals, observations versus predictions plots. So indeed, there are many different diagnostics that you can look at in Monolix to check if your model performs well or fits well your data. And I would say that the most important factor to compare the performance of two models would be the BIC, so the corrected BIC, that is the likelihood with a penalty, as I have explained previously, that the penalty takes into account the number of parameters and also the number of observations. And that is why we report the corrected BIC in Sycomore in particular to easily compare the models. But you have to keep in mind that to have a meaningful comparison, the estimate of the BIC, so the estimate of the log likelihood, should be stable over several runs. So the estimation of the model should be robust. And this is something that you can check with the convergence assessment. In convergence assessment, you can check if the log likelihood, the final log likelihood that is estimated, for instance, by important sampling, is stable. So if starting from different initial values or different random seeds, you will always get values that are very close together, which means that your BIC values is reliable. Otherwise, if you have a lot of variability because your model is not stable, then it doesn't make really sense to compare the BIC, the corrected BICs between different models. So that's for the diagnostics to compare the performance between two models. Then the other diagnostics, such as the relative standard errors and the plots, so the VPC, the observations versus predictions, the scatter plot of residuals, I would say that they are rather useful to compare in more details what is better or less good in a model. So for the RSCs, it gives an idea of which parameters are well estimated or not well estimated. And the plots show which parts of the predictions fit better the data between two models or which parts are misspecified. And these misspecifications are shown in red in the VPC and the scatter plot of residual with the VPC presets. And you can see also the misspecification in observations versus predictions. Now the next question is about the standard errors. So how to retrieve the standard errors from the file covariance estimates essay.txt. That is a file that we get in the results folder in the subfolder Fisher information, and how to draw population parameters using the covariance matrix. So this is a file that is outputted by Monolix once we have run the standard errors task with stochastic approximation, which is what SA stands for. If you have run it with linearization, we'll get the same file, but with lin instead of SA. And this file corresponds to the variance covariance matrix. That is a result of the task. While in Monolix, in the interface, we display only the correlation matrix that is related to this matrix, but that is a bit different. And the variance covariance matrix contains the information about the uncertainty on the population parameters. And so the exact definition of this matrix that is outputted in this file has changed a bit in the different versions of the Monolix. In older versions, it corresponded to the variance covariance matrix for non-transformed parameters. But now since 2021, for the two methods, so stochastic approximation and linearization, it corresponds to the matrix for the transformed Gaussian parameters. So this matrix can be used to derive the standard errors and also to sample population parameters from the uncertainty distributions. But these two procedures are not completely straightforward. So the standard errors are given already in the interface of Monolix and in the results of Monolix. But if you want to know the detailed steps that we use to get these standard errors from this covariance matrix, you can have a look at our documentation page here, where they are explained in details. But briefly, it has changed a bit between the new version and the previous ones. So before 2024, we used the Jacobian matrix to approximate the covariance matrix for the untransformed parameter based on the covariance matrix for the transformed parameters. And then the standard errors can be calculated as the square roots of the diagonal elements of this covariance matrix for untransformed parameters. But starting from the version 2024, we have changed this. We have replaced the Jacobian matrix by exact formulas to compute the variance for each population parameter. And the formula that is used depends on the distribution of the parameters, so whether they are normally distributed or log normally distributed or logic normally distributed. So now what you can remember is that we now have more precise values for the standard errors because we do not use the Jacobian matrix to approximate the covariance matrix. Then this matrix can also be used to sample new population parameters that take into account the uncertainty, their uncertainty distribution. And this is what is done automatically in Simulix when you use the corresponding population parameters elements for your simulations. But if you want to know the detailed steps that are done in Simulix to do this sampling, you can have a look at this feature of the week video that explains it in details. It's a bit complex, so I won't have the time to explain it now during this webinar, but I will let you watch it if you want more information on this. All right, now let's have a look at examples of advanced models. What are how different situations can be modeled in Monolix? And the first question is about categorical models. So in the context of categorical modeling, if a data set does not contain occasions for certain categories, so does not contain, say, observations for certain categories, for example, we do not have any observation in categories 0 and 1, while there are some observations from 2 to 6, then is it appropriate to define probabilities for those missing categories? So to explain this, let's have a look at an example of categorical data where we have here the data on the evolution of pain levels in some study on the 0 to 5 scale. But in this data set, we don't have any observation in a 0 and 1 in the category 0 and 1. We have just observations starting from 2. And we see that we have a time evolution of these observations where we have a large fraction of observations, 5 at the first time, and then this fraction decreases and we have more observations in category 2 in particular. So how do we model this and how do we handle the missing categories? The first option is to define the probabilities for all categories, but fix some of the parameters. So the structural model in this case looks like this. I won't have the time to explain in a lot of details this structural model, but briefly, since pain levels are ordinal categorical data, we write a model that uses cumulative probabilities. So this means that LP0 is a logit of the probability to be 0, to be in the category 0. It is defined here with alpha 0 and gamma t. So it's a probability that increases with time and with a coefficient gamma. Then LP1 is the probability of being 0 or 1. LP2 the probability of being 2 or less, and so on. And each of these probabilities is defined based on the probability in the previous categories plus a parameter that is estimated. And so because the probabilities are cumulative, the model assumes that the time dependence in gamma t is the same for all categories. And usually for this type of model, we include only random effects on alpha 0 and on gamma. So alpha 0 because it is the first category, it characterizes the first category, and gamma because it characterizes the time dependence that is common for all categories. But if there is no observation of category 0 and 1, like here, it means that alpha 0 should be fixed, because it will be hard to estimate, should be fixed to a very low value, and alpha 1 as well, so that the logit of LP0 and LP1 are very small. So instead of the random effects on alpha 0, we can set it on alpha 2 that is not fixed. And with this implementation, the levels, we can estimate these random effects and these parameters. And then when we simulate, we perform some simulations based on the models that we can see here on the prediction distribution plot. We can see that the levels 0 and 1 can still occur in the simulations, but they are very rare. And they will depend on the probability that we have fixed for them. Then another option is to not define these categories. So in that case, it simplifies a bit the model because we just we do not include categories 0 and 1 in the possible categories of the model, and we just define the probabilities corresponding to LP2, LP3, and LP4. So we start at category 2. And in that case, we include random effect on alpha 2 and gamma just like before. And when we simulate the model, the categories 0 and 1 cannot occur in the simulations based on the model because they do not exist in the model. So actually, it's equivalent to fixing their probabilities to exactly 0. But you see that the simulations for the rest of the categories are very similar. It's pretty equivalent. Now on the same topic, another question was, in this type of model for categorical data, would it be worth evaluating random effects also for the other parameters, so alpha 2 to 4, during the model development in order to try to improve the model prediction? And the answer is it could work, but you need to have many points per individual to have enough data to estimate the random effects. And the example that I have just shown, where you can see here the data also as continuous curves, it would not work because we don't have enough time points in each category per individual to be able to estimate different probabilities, different individual probabilities for these categories. So here it will not work, but if I had many more time points, instead of just 4 observations per individual, then I could probably include random effects also for alpha 3 and alpha 4. Then the last question on the advanced modeling in Monolix is it possible to visualize drug-drug interaction with the Monolix suite? And yes, it is possible, but it depends on the design of your study. So one possibility that I wanted to show is if you have something like this crossover example, where you have sets of measurements for 2 drugs, so drug A and drug B, that are given separately, so without drug-drug interaction, and then some sets of measurements for each drug where that are given concomitantly, so where you can have drug-drug interaction. So in that case, you can distinguish these different periods of time with occasions, so occasion 1, 2, and 3. And then you can have a DDI column with values 0 and 1, for instance, that you tag in your dataset as categorical covariates, and that you can then try to use to include some categorical covariate effects on some parameters of your model. But if your study design is more complex, then you would need also probably an implementation that would be a bit more complex than this. All right, so now we can move on to the questions on simulations. So the first question that is quite detailed is about simulating antibiotics. So the antibacterial effectiveness of beta-lactams is characterized by the time during which the unbound drug concentration remains above the minimum inhibitory concentration that we call MIC of the pathogen of interest. And so this outcome is usually written like this. So how can we calculate these two outcomes that corresponds to the fact that that percentage of time is at least 50% or is 100% using Monte Carlo simulations in Simulix and starting from a model in Monolix? So actually there is a demo project in Simulix that corresponds to antibiotic simulations that you can find in the demo menu here in the folder outcomes endpoints. So it's named Outcomes Endpoints Antibiotics T above mic.smlx. And the same type of outcome is defined there. So if you look at this demo, this is a demo project that could very well be imported from a Monolix project. So you would export your Monolix project to Simulix, and there you would define an outcome that looks like this. It is an outcome that is based on the percentage duration above some value for the concentration. And this value can be set yourself to the minimum inhibitory concentration. And then once you calculate this outcome on your simulated individuals, you can check directly on the plot of the outcome distributions that you get for each simulation groups. Here, for instance, we have 4 simulation groups defined in this demo. We can check the proportion of individuals that meet the 50% requirement that is indicated here with the horizontal line. Or if you want to calculate this proportion in Simulix, you can also select the applied threshold checkbox here in the outcome definition, and you can set a threshold of 50% here. And in that case, the result of the outcome will be the percentage of individuals in your simulation group for which you have a percentage of time duration that is above the minimum inhibitory concentration. So that should correspond to what you get. Then another question on Simulix is about the flexibility of the definition of treatments. So more specifically, for pediatric population PK simulation, the pediatric dose regimen is usually dependent on age, body weight, and eGFR. So those Simulix provide a flexibility similar to R in this kind of dose selection. So in Simulix, it is possible to define a dose amount that is scaled by one covariate, but it is not possible to combine several covariates. And if you need to combine several covariates to define your dose amount, then indeed this should be done in R, and you can easily import the table of individual doses that you have generated in R in Simulix to create a new treatment element to use for your simulations. Still, if you're interested in defining dose amounts scaled by some covariates, you can have a look at the demo named Treatment Weight and Genotype Based .smlx. That is a project in the demo in the demos menu in the folder treatments, where we have this type of treatment that are scaled by covariates. So in this demo, we have 2 treatment elements. This treatment element here that is scaled by the weight, and another one that is scaled by a genotype that is based on 2 different values. But it is not possible to define directly in the interface of Simulix a treatment that would combine scaling by the covariates and by the genotype. All right, then we have one question on lixoftConnectors, which is our R package that we can use to script the MonolixSuite in R. So the question is how to carry out a global sensitivity analysis with the lixoftConnectors. And this would be, so here we will just give some elements of answers on this slide. So in principle, you can do anything you want with the lixoftConnectors. Some starting points could look like this. So you could set up your Simulix project with the interface of Simulix to have your model as you want to explore it with the treatment design, the output design, and so on, and the parameters that you want to use. Then you could modify the parameter values. So here in this example, we show a loop where we change the values for just one parameter, that would be the clearance. But you could complexify this case to have several parameters varying at the same time. Here we use a for loop to do this, to iterate over the different values in this vector for the clearance. And in the loop, you can perform each simulation by using the function. So first, you will need to use the function load project and give as argument the name of your Simulix project in R. And then you can use this function from the lixoftConnector, define individual elements. That is the function we use to define a new table of individual parameters. So here we would give the value we have selected in this vector for the clearance and a fixed value for the volume, but you can have something more complex where you specify the different values for the different parameters. And of course, if your model has more than 2 parameters, you need to include them all there. Then you can assign your table of individual parameters to your simulation groups with the function setGroup element, using the same name here as was defined there. You have to give the name of the simulation group. Usually, if you have only one simulation group, then the default name is simulation group 1. And finally, you can run your simulation and get the simulation results with this function and store it in a variable. And then, of course, you can post-process your results depending on what you want to get as outcome from your sensitivity analysis. All right, so that's it for the lixoftConnectors. And finally, we had one question on PKanalix that is related to the new version of PKanalix that has been released with MonolixSuite 2024, which is how to conduct sparse NCA. So sparse NCA is a new module in the new version of PKanalix. I have shown a bit how to use it in an example during our webinar entitled What's New in MonolixSuite 2024 that I gave a few weeks ago when the new version was released. So you can have a look at this webinar to see some example. We will also show these features in more details in a future feature of the week video. In the meantime, you can also have a look at the documentation. And there is a demo project in PKanalix called the project sparse.pkx that is available in the demos menu in the basic examples here. So you can load this example and see how it is set up in the interface and what are the results. But conducting a sparse NCA is very easy. Basically, you just have to toggle the sparse NCA option here below the NCA button. Then in the NCA settings, there are 2 settings that are specific to sparse NCA. One is for the stratification, so how to stratify your mean profiles depending on some covariates in your data set, if you want to get several mean profiles. And the second one is available if you have some BLQ data, so data below the limit of quantification, to set up the BLQ method to indicate how to use the BLQ samples to calculate the mean profiles. Then you have to, of course, set your, as usual, all the NCA settings and run NCA. And PKanalix will automatically perform the NCA on the mean profiles that are automatically calculated. And you will see these mean profiles, for example, in the NCA individual fits. So that's it for conducting sparse NCA. All right, so that's it for this office hours session. I hope that you got all the answers that you needed and that everything was clear and that you enjoyed this new learning opportunity to get some ideas of what can be done with the Monolix suite. I would also like to advertise our upcoming events at the Page conference in Rome in June. So we will give 4 different pre-conference workshops on Monolix for beginners or for advanced modeling, Simulix, and how to use the lixoftConnectors. So we hope to see you there. And with that, I will close the webinar and I will wish you a good day.